Just 1 second.
All right, just 1 second. So, I want to start with a little bit of history. I managed to recover, was supposed to be my second slide, the conversation that we had in this very room 2 years ago, actually 23 months ago, in the JPAS meeting, and where we decided to use a series of fields which were obvious to be observed in open time. And within those fields, there was gas, M31, M87, North Ecliptic Pole, and the Kepler field. So, and a couple of these fields, they have already come up. Can I do something? All right. So, on the 28th of November last year, on the 28th of November last year, in my presentation about the JPAS strategy, I emphasized the need for a time domain project at the observatory and the need to observe the galactic plane, because the galactic plane is out of the JPAS footprint by design. So before going on, I'm going to give a little bit of nomenclature, especially, well, this was supposed to be for the cosmologists. So whenever I speak about periodic variables, these are variable stars, variable objects for which I can predict, at least up to a certain point, what is going to be their brightness in a given future. So this is like delta C fades or eclipse binaries. And I'm going to call transients objects which change in brightness without us being able to predict this change in brightness. So in this case, I'm referring to objects like supernovae or novae. I'm not going to start the story of this and why actually supernovae became supernovae after the nova. But anyway, whoever works in the transients universe has seen this plot. And so basically what we know is we've been working a lot with any time scale which is from 1 day on and at almost all brightnesses. And we are just now starting to look at transients at less than a day time scale. This, of course, removes gamma ray bursts from the equation, which are actually above this plane. But we are here to speak about JPCam, which is installed on T250. I guess anyone who's been in the observational astronomy business for some time, and students should learn this as soon as possible, you cannot separate an instrument from its telescope. You always think about them as a unique thing. And what are the strengths of JPCam? Is the wide field of view, the good image quality, and the filter set. I'm not going to get into this because we've been speaking about this the whole day yesterday, and some other people have been speaking about this the whole week. Some of us have been speaking about this for more than a decade, almost 15 years. So the problem is with the form JPCam is built, it doesn't make sense to observe one star, one point source in the 56 filters. So if you want to do a target of opportunity to observe one star, it basically doesn't make sense. It makes sense to use the wide field, for example, for electromagnetic waves. Electromagnetic counterparts of gravitational waves, like Gaston is interested in. So yeah, no telescope for target opportunity. And this is one thing that we were sort of discussing the other day. So when you, and this I stole from my own classes of observational astrophysics, when you design an observation, and more in general a survey, you have a series of parameters you can play with. But when you include the time domain part into your equation, you have to think about the cadence, and you have to think about the brightness of the object you're working with, because in time domain astrophysics, the time scale drives how often you can observe, and the brightness of your targets drives your exposure time, and hence the telescope you choose. So that, in other words, you cannot use any telescope to do any type of time domain astrophysics. And this brings me to the Nyquist theorem. It's not just observe. It is important when you observe. Remember Nyquist theorem? If you have a period, you have to observe at least twice the frequency, half the frequency. So anyway, you get the point. And we're going to get into this in a sec. So, pros and cons of time domain projects. Time domain projects normally use differential photometry. So that means you don't care if the weather is good or not. So you actually can use poor weather. And then you go and ask Stelios or Sarah or Gaston to give you the light curve, right? So if you have if you're working in an observatory, and some of us have been either telescope operators or science or support astronomers, you know that you start with a good weather project, then the weather gets bad, or you observe and you go like, crap, the weather is bad, so I have to throw away these observations. So I go to a poor weather observation, crap, the weather is bad, I have to throw this away, and then I close the telescope. But if you have a poor weather program, you go like, oh, I have a poor weather program, the weather is bad, I close. So I only waste this amount of time, I don't waste twice the amount of time. Then, but if the poor weather program tells you, oh, the weather is good, so you can go to a good weather program, and then you're happy ever after. So any observatory needs a poor weather program. This is an operational must. Now, the time domain phenomena I'm interested in are called classical novae. And what is a nova? A nova is a thermonuclear explosion on the surface of a white dwarf, which is accreting mass from a less evolved companion. There's a beautiful review from Laura Chomyuk from a few years ago, and Laura goes into this paper through a whole discussion on the physics of this, and you cannot see it, but at some point there's a question mark here where she says there may be at the very beginning, within a few minutes or hours, there may be an X-ray burst. So this paper is from 2021. In 2022, the Nature cover was about this X-ray burst detected by Hirosita, Ole Koenig, and collaborators. Explained this as the onset of the thermonuclear runaway on the white dwarf. For the past 30 years, my PhD advisor, Francesca Matteucci, has been obsessed, I hope Francesca will forgive me for using this word, with the role of lithium and the fact that classical novae are major contributors of lithium in the evolution of the universe. The lithium that you have in your mobile, your electric car, whatever, most of it comes from novae. And a significant theoretical contribution to this came from Jordi Jose and Margarita Hernans, a fundamental seminal paper in 1998. And the godfather of lithium is Sumner Starfield, who in the 1970s was already speaking about this. Yeah, all nice and predictions. We only arrived in 2015 when Akito Tajitsu detected beryllium, which in fact then decays into lithium. And hence, this demonstrates the presence. If there's beryllium, there must be lithium in our ejector. Sumner also predicted that novae can be supernova progenitors. And there's a beautiful nova, a beautiful recurrent nova in M31 Borja's not here, right?
It's online.
All right. So Borja, this one's for you. There's a recurrent nova, which may eventually become a type 1a supernova. Then there's a nova which should not be named, which we know will not become a nova, a supernova. So, you know, may or may not be. This is time domain astrophysics, so we have to speak about times. And this is a generic average sketch of a nova light curve. And the rise from quiescence to maximum normally takes about a week. There's 10 of these objects in the whole galaxy, observable in the whole sky per year. And you have to see this, which rises in a week. So this means that you need to observe. Remember, you have to observe this the whole sky every 3 days. Otherwise, you're not going to catch this. And if you don't catch the rise, you cannot catch what is the maximum, and you cannot do anything. And then the nova starts fading away. And the time it takes fading away 2 magnitudes, we call it T2. Fading away 3 magnitudes from maximum, we call it T3. This is a typical histogram. That time we've been using as a tracer of distance. And this was done for the whole 20th century. We're astronomers, time domain astronomers. We like to do scaling laws, and especially period luminosity relations and distances. And this was possibly the culmination of this work. Massimo Della Valle and Mario Livio, this beautiful S shape. And then late 2011, Kaslival and collaborators discovered this population of fast and faint novae, which sort of screwed up the whole plan. And then arrived Mike Shara and said, this is nonsense, this doesn't exist. The maximum magnitude versus rate of decline relation doesn't exist. And forgot to put the picture. There's still a beautiful fight between Massimo and Mike that is still going on. And I hope to see more of this fight. Actually, I have my own opinion. Then, when I started my PhD, also we thought there were 2 families of novae, the iron 2 and the helium nitrogen. Series of works by Bob Williams. And then Elias Saidi, in a beautiful paper, I think it was last year, no, this year already, basically demonstrated nonsense. The 2 populations actually come from the same novae, just depending when you observe them. So how do you deal with deception? We had 2 important things that we discovered that were not true. We're all expecting for the LSST, SOX. LSST, you probably heard about it. And SOX, you may or may not have heard about it. Beautiful instrument on the NTT, should come online next year. If I look at the 10 novae of last year, these are the light curves from the AAVSO, and this is thousands amateurs around the world. The different lines, they are different filters that they've been observing in, and you can see none of them peaks the rise. Assassin is an automatic survey. It has 24 small telescopes all around the world. It has beautiful time sampling. The one on the bottom right, the figure on the bottom right shows the number of images taken over the last 10 years of each field that they're observing one band in G. And you can see that they actually managed to probe the light curve very nicely, but only about 2 are very nicely and 2 blah. And then there's ZTF. ZTF is on one telescope. It's a Schmidt camera in Palomar, and it has 3 light curves. 2 are crap, and 1 is okay. The red line is the saturation limit of LSST. So that means anything brighter than that red line, LSST will not see. So that means that LSST may or may not be able to see one of these 3 novae. But remember that LSST observes in 6 filters rather than the 3 of these guys. So it may or may not be able to have the same time resolution. So for the future, Nova will keep being benefiting from projects like Assassin. And if you don't know it, crap. If you don't know it, there's a big astronomy flagship project coming online. And LSST is not going to play a major role in this science. Now, the maximum brightness of Nova is of the order of apparent magnitude, of the order of 6 to 8. But the difference between the Nova maximum and the Nova minimum is of the order of 12 plus or minus 4. This means that most novae at quiescence are magnitude 20, 21 or fainter. And guess that is where the ones who were in the JPAS meeting may remember this plot. That is where JPAS actually becomes relevant. This starts to be interesting. So when I started my PhD, this table is from my thesis. Classical novae, we were considering them as a subclass of cataclysmic variables. But then, you know, for the last 10 years, we grew up, and now we consider classical novae as an event during the existence of a cataclysmic variable. Cataclysmic variables are interacting binaries made of a white dwarf accreting mass from a less level companion. And these are 5 CVs from this beautiful paper from Elme. And if I go get the CVs from Simbad, I get the spectra from Gaia, and I get the JPAS synthetic photometry. You know, I can see structures, I can see beauty, I can see interesting things, I can see H alpha more or less wide, more or less bright. If I do the same, but instead of the JPAS, I use LSST, I see blue, I see red. So, I don't want to say that LSST is useless, but it's really not the best thing for me. CVs are all over the place, right? And these are works, I want to remark the works from Anna and Boris. But but novae are located in the plane of the Milky Way. And this is a comparison between the plane of the Milky Way and my novae, the objects I'm interested in, and JPAS. And JPAS elegantly avoids the objects I'm most interested in. Thanks. Especially beautiful, since I was the one designing the strategy. And the green line is the celestial equator. The orange line is minus 20 degrees declination. And if you take a stripe, these are around the galactic plane, those are the footprints of BFAS and IFAS. So if you take this, you can get plus or minus degrees from the Milky Way plane. You can get 1,500 or about 2,000 square degrees of survey if you try to observe down to the celestial equator or down to minus 20 degrees. The limited magnitude of JPAS are beautiful, and they're particularly interesting because I was begging Sarah for some information yesterday, and we just reached we actually grasped what's called the crowding limit. So the obvious thing to observe, in my opinion, is, and to maximize the integration with JPAS, and mostly because I'm lazy to think about different observing times and different blah, and I just take JPAS, and instead of doing it where there's nothing, you do it when there's stuff. So you cover the Milky Way plane with the JPAS exposure times, and the I band, you just use it whenever it's bad weather. Fran has kindly agreed to lead the project. This was Fran yesterday's agreement. So when I saw the presentations from Jorge and Sarah in Warwick, I was connected online. I fell in love with the field. And I was staring at the field, and I was like, okay, so these are the Gaia sources that are, okay, I'll only go, right. So these are the Gaia sources, so, and which reach, guess, magnitude 20. These are the alpha sources in I, reach magnitude 20 again. And if I were to observe with JPass in that field, I would go all the way down to magnitude 22, which is actually somewhat the limit of mini-holes. So since Javier gave us homeworks, I did it. So the rest of the strategy is fixed, right? Because I'm using JPass, because I'm lazy. So, but if I try to observe the one mini-holes field, that is just 2 square degrees. But 7 times 7, 8 times 8, I ended up 8 times 8 to have a little bit more. And it's a project which takes how much? 42 hours, which is not too bad. I'm not including I-band here. And I might have done it wrong, but Javier will correct me if I did. So to conclude, since I'm already half an hour over time, so time domain astronomy is, poor weather projects, hence time domain, is crucial for the efficiency of an observatory. Modern days projects in time domain astrophysics beg for multi-site. Unless you have something unique to offer, like sub-minute, narrowband fields, November maximum, bad business if you only have one site. Yet, cataclysmic variables, most of them, they lie after magnitude 20, and especially my cataclysmic variables. So you really want to have some JPass like in the Milky Way plane. This is, I noticed this morning, we have 1,000 square degrees for extragalactic, 2,000 square degrees for galaxy. See how beautiful, 80-20. It's a nice bridge between Gaia and Gaia near infrared, which at some point will have to get a decent name. Mini-hoax is a brilliant opportunity, and is obvious a synergy. And obviously, these kind of projects bypass the drawbacks of multi-object spectroscopic surveys. Sorry for going over time. Thanks very much.
Questions?
So I'm thinking again, already in the sky conditions. So I guess this would be a filler. So what would be, well, and I really, no? So what are the conditions required?
This is very much JPass conditions,
Okay.
but when the Milky Way is up.
Okay.
So when the Milky Way is up, which is the most distant part, like between two pairs of seeds, that is where this would fill in.
Okay, so it's not a filler. You need dark. Oh, maybe you haven't thought about that. So what are like?
For once, I don't go for filler.
Okay.
If I can write the letters to the Holy Kings, for once, I don't ask for a filler. The first time in 10 years, I don't ask for a filler.
Also, I was proposing already to be the responsible, sorry. I mean, you are talking about. So I'm happy to hear that.
Okay.
So you're mentioning that you are assuming JPass observational strategy.
Yep.
So it's a two-way to winning images in the narrow band. Are you concerned about crowding in the Milky Way? How that would impact your?
That's why I was talking to Sarah yesterday. So I'm not particularly concerned yet. So apparently down to minus 21, 22 is not a big issue.
Just a side comment. 30 seconds. I think this project worth a test because we have never observed the Milky Way with the JPass survey strategy, and there are some technical things that need to be tested, like crowding impacting the data reduction, and probably the procedure that Hector was showing yesterday. some issues related with the Curie cost and things that you may be aware of. So,
Vaguely.
it's worth it doing a quick test probably before we start making decisions about the survey definition.
That's why I was interested in mini hawks, and I think the two projects may or may not eventually merge into one. I guess there's an obvious common interest there, and can I say it? Well, I think you wrote in an email to half of the Milky Way community of Spain. So, Jorge was
replying to your email, actually.
yeah.
I was just replying to your email.
So Jorge was considering asking for some DDT time, which eventually I guess is going to be like the reply to this coming offer proposal. So I guess that is where we're going to figure out if this kind of observations is actually doable or not.
Thank you.
Sorry, I probably should have mentioned it, but since I was already vastly overtime.
Any more questions? Still, was a bit before.
Just a very quick one, because you left us with a cliffhanger. What is your opinion on the debate of magnitude versus decay time?
Oh no, I'll give a seminar about this at some point next year.
Those 2,000 square meters, exactly how you plan to choose them, which parts of the claim.
Now, if you would ask me, I would go for the Galactic Anti-Center.
Of course, because the density is lower, bad, but less interesting things there.
Now, if you would ask the PI, he would go for an open cluster. But then if you
I haven't said this.
it was the second beer. If you would go from a logical point of view, you would get one of the fields which has already been observed with mini hawks, and you would piggyback. These are the three options.
Right, we can go into the discussion after the coffee break. Thank you. Next, we have Navarro Gutierrez. We'll talk about mini hubs.
Está grabado.
Okay, good morning, everyone. And, so thank you for all the selling of mini hawks, Alessandro. Well, I think, yeah, there is a whole debate here about the crowding conditions. And but, well, before going into that, I would like you to know a little bit more on the project. I would like to brief you on the progress we have done on mini hawks so far, and then I'm going to share the talk with Sara Navarro, my student, and so I will give you a little bit of introduction and context about the project, while Sara will give you some information on preliminary results that we have obtained on the field that Alessandro just showed, and that was it was not actually a mini Hawks field. It was like a DDT that we pointed at that field in order to commission the filters. So it has several crowding conditions that allow us to test how good the photometry could be in different crowd conditions. So anyway, so the motivation of Hawks now is basically to enlarge the population of black hole X-ray transients. These systems are discovered through X-ray outbursts, so there are not that many that we know. You can see here a histogram of the discovery rate of black hole X-ray transients. In 50 years of X-ray astronomy, we have discovered 72 X-ray transients, but only a third of these systems have been confirmed as dynamical black holes. For that, you need to detect spectroscopically the companion star and follow the orbital motion of this star. So most of these systems, they become too faint in quiescence for radio velocity studies. So we are really looking at the tip of the iceberg of a larger population that we estimate is it consists of about a few thousand systems, dormant black holes in the galaxy. And it will require about 200 years only to enlarge the number of confirmed dynamical black holes by one order of magnitude. And the key point about Hawks is that we realize that there is a tight correlation between the full width Hall maximum of the strong H-alpha emission line that it forms in the accretion disk around the black hole, and also the K2 velocity, which is the radial velocity amplitude of the weak absorption lines that come from the companion star. So basically, instead of resolving the radial velocity curve of the companion star, we only need to measure the width of the H-alpha line. With that, we get information on the K2 velocity of that star. I think I'm not very clever with that. Maybe I will just use that. Okay, so I was here. And then if one combines the width of the line with some orbital period information, for example, through variability, light curve variability, then one can get mass functions, which is a lower limit to the mass of the compact star. And this is nice because only by resolving the H-alpha line, the width of the H-alpha line and this period information, then you can segregate black holes from other H-alpha emitting objects in the galaxy, like cataclysmic variables. So basically, in a nutshell, what we are doing is exploit the width of the H-alpha line as a proxy for deep gravitational fields around black holes. And what Hawks proposes is just to do a blind photometric survey in order to search for objects with very broad H-alpha emission lines. And we estimate that such a survey on a surface of 3,000 square degrees in the galactic plane, down to 21st magnitude, it would allow us to detect about 150 new dormant black holes, which is a tenfold increase on the population that we already know. So this is the idea. And then, so how can we measure photometrically H-alpha line widths? So we have investigated this problem, and then we concluded that if we combine just 3 filters centered at H-alpha with different widths, like 35 angstroms, 150 angstroms width, similar to the JPCam filters, and a broader one with a width of 350 angstroms, then by combining the flux ratios that we obtain with these 3 filters, then we are able to measure the equivalent width and also the full width Hall maximum of the H-alpha line in these objects. So these 3 filters define a new photometric system that is optimized to detect and to measure H-alpha lines, in particular the width of these H-alpha lines. The most efficient way of presenting this information is in a color diagram like this one. in this diagram, in order to guide the eye, I have plotted in horizontal lines of constant equivalent width between 10 up to 400 angstroms here. And then the curved lines represent lines of constant full width Hall maximum from 500 kilometers per second, 2200 kilometers per second, up to 5400 kilometers per second. And now in this simulation, we plot in these squares a few 100,000 field stars with different levels of reddening, and they all cluster in this area here around equivalent width 0. So this is interesting because this is telling us that our diagram is invariant to reddening and also to the slope of the spectral continuum of the objects. So no matter how strong is the reddening, all these objects will cluster in this region here and will not contaminate clear H-alpha emitting objects. And then you can see we have simulated, we have convolved our filters with other populations, other libraries of populations of objects, H-alpha emitting objects. And you can see that most of the objects, they have narrow H-alpha lines like T Tauri stars, symbiotics, and they try to cluster along the line with smaller widths. Only cataclysmic variables, which are plotted in red, because of the deep potential wells around the white dwarfs, they are able to produce H-alpha lines broader than typically 1,000 kilometers per second. And then we define a cutoff at 2,200 kilometers per second, which is very efficient in segregating black holes from cataclysmic variables. Basically, with this cutoff, we select about 50% of the expected population of black holes, while we reject 99.9% of the cataclysmic variables. And the few that lie above the line, these systems, they must be eclipsing, and they must have very short orbital periods. So they will be easily detected through light curves. So this is a nice way of segregating different populations of H-alpha emitting objects, as I said, and also selecting black holes. One thing I don't want to forget is that we have some complication here with flare stars. Flare stars are typically late-type stars, M-type stars, with deep TiO bands, molecular bands of oxide titanium. And this line, because of the properties of our filters, these lines can mimic objects with very broad, H-alpha lines. They appear in a region normally populated by black holes with low equivalent widths or cataclysmic variables with very extreme, very short orbital periods. But this is just an artifact. It's because we have perhaps some narrow emission line produced by chromospheric activity, brackets by very deep TiO bands, which, when looked through our filters, basically make them appear in this region of the diagram. So there's a word of caution about these systems. And then, obviously, we need cross-match with our catalogs. In particular, the most important are UVEX, IFAS, and UKITS, the galactic plane catalogs. This will provide us the complete SED, optical and near-infrared SED of the objects. Also, it's important to have GALEX and WISE, and of course, Gaia, ZTF, and PAN-STARRS for light curve information as well. In particular, this diagram produced by UVEX, U minus G versus G minus R, is very efficient in selecting cataclysmic variables because they appear in a region segregated from main sequence stars and white dwarfs. They are typically bluer than main sequence stars, but not so blue as white dwarfs. So these locating objects in this part of the diagram is a strong indication that they might be cataclysmic variables. But then also one has to be careful with reddening because there is some confusion. Some of these CVs might be reddened and then located in the main sequence region. So that's where it is important to have a photospectra of all the targets in the field, because this is a nice way of segregating different populations of breaking the degeneracy with interstellar extinction, and then identify, for instance, Miras or objects with very deep molecular bands or emission-like objects. So it's really, we see a strong potential of using, of obtaining photospectra of all the stars in the Mini-Hawks field. Well, Mini-Hawks already started 2 weeks ago. Mini-Hawks is basically a pilot survey of a small patch of the sky of the galactic plane. Initially, we decided to divide this into windows, one in the winter, another one in the summer. The 3 filters have been built and commissioned. Sarah, after my talk, she will continue and will explain preliminary results that we have obtained in one of these, commissioning observations of the filters. And we expect that Mini-Hawks will deliver a few hundred cataclysmic variables, a few thousand H-alpha emitting objects of different classes, and perhaps 1 or 2 black holes. We still don't know, but in order to discover a significant amount of black holes, we need to survey a much larger region of the sky. This is the footprint, the initial footprint of the winter window. We have basically maximized the declination in order to get best visibility from Javalambre. We are also constrained by a galactic latitude between plus or minus 5 degrees in order to overlap with IFAS, UVEX, and UKITs. And well, this is the window that we have defined. 2 weeks ago, we had the first pointing at galactic latitude minus 4 here. This hasn't been completed yet. And why we selected that? Well, to start with, we want to overlap with IFAS, UVEX, and I said UKITs in order to have a continuous optical and near-infrared SED. Also, this region here has coverage by GALEX, which is very interesting in order to identify CVs, ultra-compact objects, white dwarfs. And also, to conclude, if one looks at reddening maps made by IFAS, the window we have selected in galactic longitude has a very low extinction. So it allows us to survey a very large volume in the galaxy and therefore go deeper and then try to detect more objects. And I will stop here, and then Sarah will show you the results of the commissioning of the filters in a particular field in the galactic plane. It wasn't in the anticenter of the galaxy, but it was in a region with significant crowding. So she's going to tell you about that.
As a commissioner of the filter, we applied for a DDT in Javalambre to observe part of the galactic plane, which contained the globular cluster M71. We chose that field because to test the observing strategy, and because it's a good way to test the extraction method under high crowded conditions. This field have also observation in ultraviolet and X-ray, and it's overplot with several catalogs of variable star and with surveys like IFAS and UVEX. And also this field has 2 known cataclysmic variables with high emission in H-alpha. So the DT consisted in 7 hours of integration to reach a signal noise ratio of 15 at magnitude 20. We divided these 7 hours in 40 cycles of our filters, and we also observed 10 exposure in the Sloan filters for calibration purpose. And as we see, there is although it's a globular cluster, is one of the least centrally condensed. So to make a root calibration of the colors of filter, we cobalt the Picker's main sequencing spectra with the transmission of our filters, and we represented in orange the resulting colors in our H-alpha color diagram. We also plot in black the brightest star of our photometric result with magnitude less than 14. And we can see that there is a shift between the stellar locus of Pickers and our data. So we calculate the offset that minimizes the distance from the clouds or clouds points to the Pickers spectrum. So now I will show the whole results. I divided in bins of magnitude to better show it. These are instrumental magnitudes, and I also plot contours of equal density with 1, 2, 3, and 4 sigma, which 4 sigma of the total of stars, which contains the total of stars. And in the first bins of instrumental magnitude, we found 3 Mira's variables, 1 carbon star and 1 Wolf-Rayet. If we go deeper, we found one of the cataclysm variable that we expect to find. If we compare the frames in one of our narrow filters with the Sloan R, we can see that it's brighter, this object, if we compare with the nearby stars. So it has a clear emission in H-alpha. For that object, there are only 2 spectra reported. One in a quiescence state and one in an outburst state. We know that we got that object in a dormant state because of its magnitude in R. And our values of photometric equivalent width and full width and maximum meets well with the values that are provided in the paper of Ramsay et al. With the spectrum. So if we go deeper, we found the other cataclysm variable, which there isn't a spectra reporter for that cataclysm variable. And the H-alpha emission is weaker, but still broad for that object. This is the last instrumental magnitude bin. We are at the level of the noise, but we can see that we're still able to separate objects with more distance than 4 sigma from the clouds point. So we found a lot of interesting stellar populations: 3 Miras, 1 carbon star, 1 Wolf-Rayet, and 2 cataclysm variables. There are 13 unknown potential emitters in H-alpha. So we apply for DDT in the GTC to have a spectra with Osiris to understand why these sources are in that region of the diagram. First, we observe the 2 cataclysm variables that we can see clearly the double peak, the classical double peak H-alpha emission. The Wolf-Rayet have a tiny emission in H-alpha, but it's not H-alpha, it's a blended of carbon 4 and helium 2. the carbon star have a thin emission in H alpha with broad absorption bands. And we observe two variables mirrors with have broad absorption bands, the oxidotitanium, which simulates an emission in H alpha and will contaminate the region of candidates of black holes. And we also observed two potential black holes, but finally this seems to be an active dwarf. They have an emission in H alpha with broad absorption lines that simulate a broad H alpha line. There are a lot, but there are still objects that we don't know what they are. So we look for spectra in Gaia for the brightest unknown objects, and we found that 3 of them are M-type stars with the broad absorption bands. And we are in particular interested in the target 8 and 9 because they are bluer than the others, and they seem to have a tiny emission probably in H alpha, and they could be a G or early cat type or a Redenet B E star. And so we need more information to classify all of contaminants in the region of black holes candidate. So as Jorge says, one tool is the color diagram of UVEX, where we did some tests and we found the two cataclysm variables that we expect in that field in the region that that we expect to be in the color UVEX diagram. And finally, to conclude, we successfully tested the mini-Hawk strategy. We obtained from photometry of 2 square degrees a million stars, of which 20 are potential H alpha emitters. We found a variety of different stellar populations like cataclysm variable, well-rayet, carbon star, Miras, and active M dwarf and Redenet B E stars. We have a solution that we didn't expect, that the Miras and active M dwarf contaminate the region where we expect to find black holes. So we need additional tools such as JPCam with the photospectra to help to classify and clean our sample. And that's all. Thank you.
Questions for Bob?
But yes, I have surprised that you have found variables that actually you have showed us the absorption bands actually look like emission. Just probably there is a way to don't have this kind of sources, just looking for variability. So probably Gaia has provided the light course of this kind of stars. So you don't need to go to the telescope and take a spectra for these sources.
But it depends on the brightness, no? Because if they are very faint, then Gaia cannot provide these light curves. Yeah. I mean, what we are finding is a lot of these contaminants, they are very faint, Myra or N-type, active N-types. Yeah, start. Yeah. But then you got a good point. Yeah, if you get the light curve information, this is another way. In addition to records.
Vista has variability information.
Yes.
Sources are very bright.
Yeah, the videos are long though, like hundreds of days. No? So you need a very good coverage.
Yeah, but if they show a large variability, even they have not the complete figures.
Yeah.
I mean, you can just identify this by the large variability.
Okay, thank you.
Actually, I had a curiosity, which is somewhat related, because you guys commented using Galax and Wise.
Yes.
And these are, in general, shallower, well, sort of depending on the wavelength range you're playing with, they're shallower than what you would get in the optical. Or, in other words, how much does the use of these ancillary data affect your search?
I mean, Wise, well, there several versions, like all Wise,
Yeah.
one Wise, they cover the entire sky.
But they go deep enough.
They go, yes, they go quite deep.
Yeah, my concern is the depth.
Yes, they go quite deep. And Galax, they go 22,
Okay.
minus 22. Especially in the near UV.
I have a more technical one. It is not completely clear to me. In the end, you for the source extraction, you use your own method for the more crowded regions of the images, or do you use the catalog that you already provide?
I use DALFO to the subtraction.
Okay.
Yeah.
Yes.
This is the real thing.
This is, well,
And you are happy with the results?
Yes.
Yes.
The cluster,
I have some plots
extra
just to get an idea to the quality of the subtraction, but we are still working to perfection that. But we think that we have a good result. Well,
Yes.
we are going to have a good result.
yes.
May I do a comment on this? That you shouldn't be scared of pointing to the plane fields regarding doing the reduction with extract or similar. In many surveys that they do the galactic plane areas, they don't do PSF photometry. They do like optimal aperture photometry, just taking into account that they are going to lose many objects that they are blended with other stars. The main problem will be in the radar bands. If you are really looking to the plane, from experience that in R band or in the blue, you don't have so much ground. But when you move to the I band, the number of the stars that appear is huge and becomes a challenge. That would be the main problem if you use extractor for photometry in the radar parts. For global clusters, you need DAO. Our interest, as we know from many black hole candidates, you might have interlopers, and we want to recover the maximum number of objects, not to miss the chance to discover a black hole binary, basically. But I think you have the tools to get good results, and also if you make available the data to the community, as you do, they can play with DAO if they wish to recover some interesting source.
Time for one more question, either here or online. Dennis?
I probably didn't get it. It's still too early. I only had one coffee. So, is this test field in IFAS and UX and Y and so? Do you have SEDs of these candidates that you have? The question is more, how much can you use these SEDs to refine your candidate list before you go to GPC? Or how much dependent are you on the GPC at the end of the day?
Oh, yes. I mean, we have overlap with all the galactic plane surveys, because this is a field that has a galactic latitude of -4 degrees. So yeah, I mean, this is just like a quick and dirty analysis. We basically did the photometric analysis and the color diagram, but then the next step, as you said, would be to look at all the complete SED of all these objects and in order to see if we can constrain the spectral types and classify them before doing spectroscopy. But since there were only 20 of them out of a million, then we thought it would be interesting. Also, we wanted to do the exercise of getting the spectra and now convolve the spectra with our passbands, filter passbands, in order to get synthetic magnitudes and see how good they are compared to the magnitude that we get through the filters. It was another motivation for
as you say, it's only 20, but if you get 20 in your one pointing, which by the way,
that's right.
it clearly works and awesome results, but you know what you're going to expect in your second and third and fourth pointing, right?
Yes,
And your list of candidates will start growing very fast.
Yes.
So it would be interesting to see how much
Of course.
more Sarah can do on selecting.
Right. We can continue the discussion after the coffee break. So let's move on to the next topic. Just like to speak. Next speaker is Eduardo Martin. Talk to us about JST250 Euclid substellar science images. You only have 10 minutes.
Today, I would like to tell you about substellar science in the context of Euclid. That is a space mission that was launched last year, and we are getting data. You will see during the presentation what Euclid is providing. And I hope to convince you that it's very important to, I know that JPAS is doing part of the Euclid surveys. So today I hope to tell you more about that and what the future could be. So first of all, let me explain a few things about substellar objects. Substellar objects are providing a bridge between the planets of the solar system and the stars. We see a continuum of properties. The substellar objects, when they are young, they can look like red dwarfs, but since they do not develop thermonuclear fusion, they keep cooling down, shrinking, and they get to extremely cold temperatures, covering the whole range of temperatures that you can think of. So they provide us with new properties, for example, different type of clouds, and a range of colors. As in this diagram, you can see how the objects, as they become fainter, they change in color because of the condensation of dust particles in the atmosphere, clouds shrinking, and then the formation of molecules such as ammonia and water. The number of substellar objects is increasing. When I started my PhD, well, actually in '94 I was finishing it, the number in the solar neighborhood was 0 within 100 parsec. And now it's about 25% of the population within 100 parsecs. So this is a very important by number population of objects. Euclid is a European-led space telescope. It's a survey telescope, a wide area, and it covers the visible range with imaging, high-quality imaging with a 0.1 arc-second resolution. It also has near-infrared in 3 filters with the worse resolution, three times worse than in the optical, 0.3 arc-seconds, and it has a slitless spectroscopy as well. Euclid will mainly cover the extragalactic sky in the wide surveys. It also has 3 deep surveys, 1 in the northern hemisphere and 2 in the southern hemisphere. As you can see in this image, Euclid, like JPAS, avoids the galactic disk. In the first science program of Euclid, we managed to include a few fields in the galactic disk, providing some of the very first science coming out from Euclid. You can see these fields over there. Let's see if I can get the pointer. Well, they're here. So around here, in blue here you have, this is the coverage of the Euclid deep fields and the wide fields. And these are in particular the fields that we were selected to cover with Euclid as an extra that was only done for the early release observations. Of course, there cannot be any presentation about Euclid without nice images. These are nice images that were produced for the early release press release. And the color one is one of our fields in the iconic Horsehead Nebula. We choose this field because it's a very well-known giant star-forming region in the Orion constellation. And here you can recognize the same constellation, but this is a view that shows the star formation. And that's a Euclid field. You can see it's big, but it's small compared with this giant star-forming region. So we have focused on that. And we made a division, a separation in this Euclid field between low reddening region and a high reddening region. Because Euclid is a new facility. It has a new photometric system. And we were working in the beginning with uncalibrated data and then learning how to calibrate it. So to keep things simple, we started with only the easier half of the field of view that actually covers part of the Sigma Orionis cluster. This is a very young cluster that we have been studying for over 2 decades. So we had some good benchmarks in this region that we could match with the Euclid observations and try to calibrate and guide our search. One of the things we did was to do strong filtering for point sources. So we eliminated the majority of the sources that were detected because at this depth, we are dominated by extragalactic sources. And at the angular resolution of Euclid of 0.1 arc-second, we could see that they were resolved. So that interval is the narrow interval where we selected only point sources and we decreased by a lot the contamination. From pretty much a scatter plot in the color magnitude diagrams and color diagrams, we were able to clarify things. Another thing that is coming from the high spatial resolution of Euclid is the possibility to detect companions. In this particular case, we have detected a possible planetary companion to a planetary primary. So I'm not sure how to call that, but well, that's what it is, a candidate planetary mass companion around a planetary mass prime. We were able to make, after this filtering getting rid of most of the detections in that field of view only that I show you are in about 300,000 sources. In this same field of view, Gaia detects only a few thousand sources. So Euclid is really very powerful and provides an incredible amount of data. So in this color magnitude diagram, you can see a clear separation between the cloud of objects mostly in the background of this Simorionis open cluster. And then in color, you can see a nicely defined sequence of objects that roughly agrees with an isochron. That's an isochron at 3 million years of age. The agreement is not perfect, but the isochron provides a good guide. In red, you have the benchmark objects. The benchmark objects are objects for which we have been collecting ground-based spectroscopy with the GTC, with Keck, with the BLT over many years. So we are very sure that the red objects are ultra-cool substellar objects. And you can see then that these red objects are in this sequence. Then we also have the green objects. The green objects are candidates that were published in the literature, but they did not have spectra. So we confirm a number of them as being on the sequence. And we have the blue ones. The blue ones are new discoveries from Euclid. And in particular, you see the blue ones extend the sequence a bit down to the even lower planetary masses. So that is a part of the first batch of science papers with Euclid, and that is going to be a special issue of Astronomy and Astrophysics. And then this is work in progress. This is another field of the same program, the early release observations, and this one is in Taurus star-forming region. Taurus is an example of dispersed star formation. It's a different mode of star formation. Orion is more like the type of star formation where you have a cluster forming, you have a giant molecular cloud, but in Taurus, there are no clusters. There are only associations of T Tauri stars. There are not any O-type stars in Orion, yes, in Taurus, no. So these are representative of two different modes of star formation. Taurus is also more nearby. It's about a factor of 3 closer to us than Orion. And so, because it's closer, with the same depth, we can get to lower planetary masses. And in fact, what you see at the bottom is 1 Jupiter mass. So in Taurus, we can get to 1 Jupiter mass or even a little below. If we can control the contamination, in the first work in Orion, we had to throw a lot. We didn't go to the sensitivity of Euclid because of this strong filtering. And in Taurus, with this strong filtering, it's applied here, and we're getting to 1 Jupiter mass. We could get to almost a Saturn mass if we are able to improve the control of the contamination. These are color diagrams of the same Simorionis field I showed you. The upper one is the color version of the color magnitude diagram. And you can see again the red points define a very clear locus in this diagram. And we have the blue objects in that region, the new discoveries. But in the other half of the diagram that we avoided, because that's where we have the high extinction, variable extinction, all of that, then you can see that things are a lot more complicated. Our red objects are there, okay, just for reference, but they are not in that part of the diagram. We just put them for reference. But you can see in that part of the diagram is not as clean as in the upper part. When there is reddening, things get messy. And then we have a lot of things that could be candidates, but at the moment is pretty much work in progress to understand how we can deal with that. We also have other regions in Orion. This is a double cluster that we are working with, and we have zillions of detections with Euclid. And we are in the process of identifying candidates and trying to understand how to segregate these candidates from redden background sources. Another nice picture of Orion. And this is where we want to get at. What we want, our main science goal is to extend the determination of the initial mass function into the planetary mass regime. And this preliminary result is in the Sim-Orionis cluster with the Euclid data, and we compare with solar vicinity within 20 parsec in the planetary mass. So you can see that this is mainly substellar masses in the upper part. This is in Jupiter masses, starting at 70 Jupiter mass. So this is discovering the very low mass stellar part, the substellar limit, that is around 70 mass of Jupiter, and then down to 3 Jupiter mass in this case. We see that the shape, when we compare, like doing this fits to the data, we compare with the solar vicinity, and the agreement is not so good, but still a lot of uncertainties in how you do this. So this is a lot of work in progress. But today I want to tell you about a new thing that we have realized. And in this plot is quite clear because in this plot there is a histogram for the Gaia sources for which we can determine membership in the cluster. And you see them, and they are covering the stellar part mainly, and they stop at the boundary between brown dwarfs and stars for this particular open cluster. But if you change to another open cluster with a different distance, different age, this will also change. But for this particular open cluster, it turns out that the Gaia is useful down to close to the substellar limit. And then Euclid really starts to contribute in a very complete way in the substellar part. And what I call the gap between Gaia and Euclid is the region in between, because the region in between is when the Gaia is not providing very good data. It doesn't have enough quality for the photophotometry, for the parallax, so it's not good enough for membership determination. And Euclid is saturating or non-linear. So we have there a range of magnitudes that is difficult to work, and it's very important to have a continuity in the determination of the mass function of young clusters and star-forming regions. So, and that's what I'm going to tell you today. That's where the new facility here can play a significant role in covering this part and helping to have a continuity in the studies of the initial mass function in these nearby star-forming regions and young open glaciers. So these are again showing you the Euclid wide area and surveys and deep surveys, and they are completely avoiding these very young regions, as you know, and it has been discussed here that this is important to investigate in the regions close to the galactic plane. So this is another science case reinforcing the importance of studying that. Gaia is estimated to be complete up to 100 parsec, so that in this picture Gaia is here. So it's Gaia for ultra-cool dwarfs of the latest M spectral type is limited to our solar vicinity within 100 parsec. Euclid is reaching much beyond, is reaching to significant galactocentric distance for very late M and L type, and even for T type. So Euclid is really going very deep. Gaia is shallow, and we need something in between. This decade is revolutionary for the increase in the number of substellar objects, in particular for the mid-L type. We're going to witness order of magnitude increase in the number of objects that is going to revolutionize this field. The same as it happened decades before with very important surveys. So now it's mainly the era of the new wide surveys, and in this field it's going to be extremely important and very timely. Euclid is an amazing technological challenge, and also Euclid, from the point of view of big data, is very big. Euclid alone is going to provide more data than all the space missions before history. So it's really like a new game, and ESA is adapting for that. But now at the beginning of the mission, we're having serious issues with the data management. In the general context, this work on the initial mass function is also connecting with other techniques such as microlensing, that is probing with in the galactic bulge, is probing a population of free-floating planets, and this is actually coming from a work published last year from microlensing, and they are claiming that there could be a significant increase in the population of free-floating planets, so much that they could be more numerous than stars. This is something that is based on low number statistics, but certainly is going to be very exciting to try to get as deep as we can in, and as low mass as we can in the nearest star-forming regions to try to cover with this technique this part of the initial mass function. In collaboration with Pedro Mas Buitrago, Enrique Solano, and people here, we already started with the discovery and characterization of ultracooled dwarfs. So we are familiar with this type of survey you have here in Cabalambre. This paper was published a couple of years ago, and some objects from that paper we have been following up with the Nordic Optical Telescope. Now there is a new draft, and we have been able to confirm spectroscopically that J+ is giving very good candidates with high fidelity for ultracooled dwarfs. So I think we have this in quite a good control. And in that work, it was possible to detect objects for the late M-type up to several hundred of parsec. And the dashed line here is the division between M-type and the cooler spectral types, L-type. So for L-type, then the telescope is small, and we did not detect so many. So the previous number of objects that were coming from infrared surveys was superior, but this is because it's a small telescope. But with a bigger telescope, it can be competitive in this part as well. So I have made here a summary of synergies that I foresee. First is that with so many filters, it's a kind of low resolution spectroscopy, as Jorge mentioned before, then you can have an optical characterization of the ultracooled dwarfs. Also, the chromospheric activity can be detected because of these filters in H-alpha and calcium-2. These emission lines are also important to detect accretion activity, active accretion in these young regions. It can also help us with getting a high resolution reading maps. This is going to be very useful to have an extra control on the contamination of the background. And the most important aspect that I foresee is to fill this Gaia-Euclid gap in the ultracooled dwarfs. Okay, well, thank you.
Questions? Right? Nothing? And we are exactly on time for coffee.
Perfect. Okay. Before you leave the meeting, please return the plastic to the back that is in the elevator, please. And second announcement is just for the people that go to the observatory tomorrow. So it's the 4 people sit here, and you go by your own car. Then there is Paula, Ignacio, and another person, and also Evgenia. I don't see it. Okay, somebody tell me. And is there nobody is joining us?
I didn't sign up for the university.
Okay. There is a place for one more, probably. What?
I have a car.
No, but don't worry. But and is Borja here?
It's online.
It's online. But the problem is that there is a place for one more, so it's all well.
I can do that.
Okay. Well, but the place is 9 o'clock. 9 o'clock. For those that Evgenia, Paula, somebody tell Evgenia, and you 4, and Ignacio. See you at Paseo del Óvalo at 9 a.m. Okay.
You cannot park.
Yes, in fact, you cannot park there. If you have problems, just go wherever you can park and I will check with the streets now.
I mean, we cannot party tonight.
Ah, no, well, we can because the person who drives cannot.
Rossana doesn't show Manuel in the
See you after the
¿Quieres dejar tu portátil ya?
Bueno, se me queda sin batería. Se acabó. No, pero si no,
No, pero enchúfalo, bueno.
prisa. Si tenemos tiempo de sobra.
The discussion is for
Yes, and I will. So the next session I will lead. Don't worry. ¿Quieres internet o...? Sí, mejor. Porque luego, no para esta a lo mejor, que también, pero para la siguiente.
Sí.
Batería. No, yo creo que aguanta. Y si no, luego lo conecto yo.
Bueno, me voy a por un zumo.
Venga, vale, avisa a la gente entonces para que entre, ya que va a ser. Sí, gracias. Venga.
Sí, sí, sí.
Please sit down. Javi,
Sí, vamos. Ya, a ver. Claro. Vamos a ver. Es que así termino mis puntos.
Que conste que yo he hecho mis tareas.
Bien,
¿Viste?
bien. Please, take a seat. Voy a comprar. Ya tiene que levantar. Está bueno. Sí, ya lo sé, no hacía falta que me lo dijera.
No, es que para que notes.
Claro. We are going to start the discussion. Okay. Thank you. Hello to the people online. We are going to start with the discussion. I have here a few points written that I would like to discuss in this order. So about no, sorry for the people online here. People is not listening. So I'm going to stand up. Okay.
This is complete anarchy.
Yeah. Okay. Good. So, people online is I cannot read what is online people saying, or maybe can I use this? I don't know how to
You don't
use.
want to misbehave.
Okay. Okay, okay. How can I use this to read the messages? I don't. This is not.
Well, you probably cannot read the messages there.
Okay.
If you want to read the messages,
Okay.
you come here.
Okay.
What is the mouse here?
You have
to come here.
Then first you should ask yourself, do you
Chat.
want to read the message?
Yes, I want.
Here you
Of
have the
course.
chat, but if
Okay.
you have like this,
Okay,
Maybe-
perfect.
I put it here,
Okay.
so you have to look there.
Okay. And well, and people online, if you want to talk at some point, maybe speak up because you are only 6, probably less. So just if you want to say something, speak up when you see that there is no one, or raise your hand and wait until Juan gives you the word. But maybe we don't need. You can just participate as you want. We are going to listen to you. So the first point I would like to mention is other science cases that maybe were not mentioned. I have mine, but I would like to maybe to see if someone online or here has another science case that would like to discuss here. No? I know. No, Rana. I'm looking at Rana because okay. So please, Rana. Rana is going to talk about the science case.
Hello, I'm Rehana.
Yeah.
Talk next to the mic.
But you can.
Hello everyone, my name is Rehana. I'm a postdoc at CEPTA. With JPAS, I am working on a Lyman Alpha Nebula around high redshift QSOs. So I have a suggestion to have, like, my science case is really depends on the deep observation of JPAS and also different filters which cover the emission line. So if there is a chance to get the deep observation, I can have like more productive science, my science case. So actually we are missing the we talk about we can do IFU like science with the JPAS with multiple filters, but we are lacking to trace the diffused emission and also emission line properties. That is, we are just taking the very bright object with the JPAS, with the shallow observation of JPAS. So I was this in my case, I was having some target which I want to confirm it's extended emission, and JPAS was the best tool to do my science. So if I'm planning to propose for a proposal and to get much deeper observation, and I know they cannot change the filter tray, and so some of my target can fit with the existing filter. So my question is I have a suggestion actually to give some part of time to deep observation to trace the diffused emission of galaxies as well as the for example Lyman Alpha extended nebula around high redshift cases. Yeah, so is it otherwise we are lacking some of the most important science. Most of the people are doing with the catalogs. We are the only few people working on the images. So deep observation is very important for us. Yeah.
Oh. Someone has a question for Rana? I have. So for the first question is how much area would you like to have in deep and contiguous area?
Yeah, actually, I have a large sample of galaxies QSOs. So if I have with the one filter array, I can right now I have some candidates that can within one filter itself. One CCD, I can finish my observation. But even though it is other filters which is covering with other redshift range also can give I can get the science from that also. So even one observation itself, I can get the science out of it.
Thank you, Ran. We have internal discussion because this is related maybe with JPAS or even the observatory, that there is an opportunity to maybe to go deeper, but well, we will, because it's internal, we will, this is something to be discussed, I guess,
Yeah,
here.
sure.
It's not for open time, also the possibility to go deep.
Okay, sure.
Okay, and the tools are there, so just explore, and if you need help, explore how much time you need to go to the depth you want with the pressure time. If you need help, ask now the expert of using this tool, and or we will use maybe in the next session. All of you are now experts of using the tool. Well, we will use it maybe after this discussion. We can use it to check how deep we can go and how much area. Okay, thank you. Maybe another science case. I lack, in my opinion, we lack a nearby galaxies proposal or idea.
That's an interesting one.
Well, yeah, that's right. Well, more nearby galaxies. But this is almost Milky Way. I don't know. Anyway, but so I encourage the people to think in those cases. We have at the end, in my case, I have discussed this with individual people. But well, if someone wants to speak now in remote or hear about an idea with nearby galaxies, I know that it's difficult because nearby galaxies are not that large, and within the JPAS, we are going to observe several nearby galaxies. So we will get what we want at some point.
What about the Virgo cluster? It's one of those obvious things. Has anyone thought about the Virgo cluster?
No?
Like Virgo in JPAS mode, for example. Would it be any use?
So slightly deeper.
Or slightly deeper.
Well, I think it's interesting. But maybe we can discuss this in a smaller meeting or people can just live by themselves. No, I mean, I encourage people to ask for these observations. Okay, so let's move. If there is no one talking about other science cases, let's move to the. Okay, yes, Tony.
It's not a science case. It's a general comment. What I'm missing in this meeting is proposals for filler programs.
Sorry,
so I had all my hopes in Alessandro's
yeah.
I mean, we saw your talk yesterday, but I think that I encourage people to think about these kind of projects because the lower the weather condition requirements in your proposal, the higher the chances are going to be to get a significant, a larger amount of time. So now, so far as I understand, we have David's program that can be executed in more any observing conditions. No. Okay. No. So we need even more filler programs to be figured out. So this is just an idea that I encourage the people here and remotely to think about projects that can be executed in different observing conditions, because at the end, this time will be available, and the pressure, as you can see, as a result of the discussion that we are having in this meeting, the pressure is going to be lower. So this is just sharing with you a thought.
Yeah, that's right, Tony. I have. So we encourage the people to think in asking for filler programs, because we know that the pressure is going to be higher in good conditions, and we are not going to be able to observe all the programs asked or proposed in the best conditions. Okay. Okay. So next point is I would like to talk about the distribution of filters that we thought yesterday. Tony had the idea of the possibility of changing or doing a new tray, or even more than one tray. So I would like to ask you, not now, but you have to think which filters would you like to have in the same tray. And of course, you can ask for 14 filters, but it's easier, for example, now that Borja is here. It's easier, for example, now because we had the idea from yesterday that David and Borja, maybe they think, or they can discuss what are the filters they have in common and what are the filters they want, and maybe they cannot use, or they don't need the 14 filters, but just 5 filters each, and then we still have more, more, the 4 filters more for another project. Anyway, just think how much or which filters would you like to have in the same tray? Yeah.
Just to clarify, so what you are mentioning is to use the copies
Yes.
of the filters that we have from JPAS
Yes.
to configure a new
Yes.
tray that could be more custom.
Exactly.
Question about
Yes.
once this tray once this tray is configured, how long will it be? Like forever or for the project duration?
For the 1 year that we are observing. So it is for the call, right? Because after that, there will be an additional call and probably different projects maybe selected. And that time depends.
My question is, it was more if it was going to be like a longer period. It's just the duration of the call.
I mean, we haven't talked about that in detail, but my quick answer is that the scope of this potential trade configured with a particular set of filters that are needed by a particular project or projects for this code. So the scope of that trade is only for that code, because the needs and the requirements for the next code may be similar or may not. So, but once the tray is assembled or integrated, it will last for the whole year. So what we are not doing is start changing filters from one tray to the other during the length of the observations.
I think something to point out here is like the camera has 5 slots for trays.
Yeah.
So we would be replacing one of the JPass trays with this special tray.
We can, well, let me just be clear, because this is a matter of confusion if you don't know the instrument and how we operate at the observatory. So what we are not doing is changing filters from one tray to the other, because this is a complex and with a non-zero risk activity that needs to take place at the observatory clean room. So this is critical. But once we have the trays, you are right, JPCam allows for a simultaneous integration of 5 filtered trays. But now it has the 4 narrowband JPass filter trays plus the I-band. But the system has been designed to make the filtered tray exchange during the day in a not easy, but something affordable way. So at the end, if we have not only the 5 JPass filter trays, but imagine that we need another broadband filter tray and this newly defined filter tray, so we make 7 or even 8 filter trays. What we have to do at the observatory level is to plan the observations. So, and say, okay, this week JPass will be observing with tray 1 and tray 2. So we remove 3 and 4, and we use those slots to add the open time tray. So I wouldn't be worried about that. Assume that we have 8 filter trays, 7 filter trays.
Yeah.
And then we can, the 2 that are not JPass filter trays can be, one of them can be configured in that manner. But filter tray exchange is possible. Filters inside a tray is not possible.
Yeah. My point was about the duration of the custom filter tray along the year. So just to make people aware that if JPass needs the 5 trays, that it will be like a period of time. We will not have one of the JPass trays for this.
This is part of the observational strategy and the planning. But JPass is not observing with the 4 trays during the same night.
Right.
So in fact, JPass is observing with 2 trays for a couple of weeks, and then we switch depending on the home phase, to the other two trays. So we are talking about a tray exchange rate in JPass that may happen every 2 weeks. So if those additional trays for open time are required every night, I mean, this is something we need to discuss internally, and the result will depend on the particular projects that are going to be observed. But I mean, you have a lot of parameters and variables on your mind. Let's keep that one. So let's assume that the filter tray will be available when they are needed for the project. And this is Javier's job to make it happen.
Well, I think it's possible. I mean, I don't think, well, I think it's possible, but yes, but then of course the path department, which is the one that reduced the data, also needs to confirm that this is possible. But from the observational point of view, is possible. But I mean, it's still not people have not asked this. So let's begin with David, Borja, or whoever wants to maybe design a tray and then check because maybe there is no need. And just also it's important that we can just put 4 blue filters in the tray, just 4. And I'm not sure how to define blue. Maybe Hector or Tony.
Well, there is some constraint in JPass, but I think, again, it will depend on the science case, no?
But there are some technical constraints on what filter can be installed at the same time and what position within the hardware. Because there are some, I mean, I don't want to spend much time. You know that an interferometric filter is a mirror, right? So we have 14 mirrors in the optical path. So there are a lot of reflections. Part of those reflections are removed by the filters themselves. So the filters have been designed to remove part of the reflections at a certain wavelength. So they require some particular distribution within the filter tray. So there are a lot of possibilities, but some possibilities may not be valid from that technical point of view. So the same advice as we discussed yesterday. If you are thinking about configuring a new filter tray with 14 JPass filters, let us know as soon as possible and allow us to be part of the decision process so we make sure that all the technical and scientific requirements are fulfilled.
Yeah. So please, so David, Borja, and Rana, you should talk and decide a new tray. And
they talk to me.
Okay. And people in remote or here also, if you know, if I myself, if I have if I want a filter, I would try to also to join the conversation, which will lead, I guess, because here in CEFCA we have 3 persons already interested. We will lead here, I guess, but please join the discussion right into us. I guess this is all about the distribution of filters. If there is nothing else. And then last point I would like to discuss is, well, I'm going to repeat ourselves, but if you need a special observing mode, contact us. This is the right moment. If you contact us when we open the call for proposals, maybe we are not going to be able to. We will not have the time to discuss the feasibility of your special need. Special need that I can imagine is different pattern, especially in the narrowband strategy. And then I took some notes also, and this is the first one. So if you need a special diesel pattern and open filter, we are almost sure that we can do it, but there are also some technical difficulties. So if you are going to need that, or if you plan to propose open filter, maybe Adriano was yesterday talking about this, and I think today is not okay.
I wanted to comment about this special case, which is still a special case.
Yeah.
But maybe it has not been commented. Personally, I'm for this. I like this
Yeah.
this type of observation, but this is not important. The question is that there is an advantage with this open configuration because you get more area because there is no vignetting, or the vignetting is much lower.
So should we put, sorry, Hector, should we put a tray because I'm not sure about that.
We can even work without putting a tray because it's not even needed.
What?
We don't need to put a tray. We don't need to place an empty tray.
Okay, now a question for Tony and you. Are we able to focus or to align with the auxiliary detectors or even align? I mean, maybe I should know this, but I'm.
I guess
This
that's
is
the
the
case.
question. This is when we say, when Hector says that we haven't tried that,
Yeah.
it's that because we need to test that. If we don't, the optical design is taking into account a filter, so that is in the converting tip, so that impacts very significantly the photo. So we need to test, and this is something that is in the to-do list, to test if we can actually focus the system without filters on one side, and on the other side, if we don't have filters, we cannot use the auxiliary detectors to do the image quality follow-up in real time.
So you need to place
the two aspects that we need to understand. Whether we can focus the system because of the stroke of the actuator system and the secondary mirror hexapod on one side. And the second thing is that if there will be a significant overhead because the optical alignment during the observations will have to be done with the scientific CCDs instead of the auxiliary one. So this is something we need to test and we need to validate, and the overhead for this particular case needs to be estimated.
No, please continue about the area. Sorry, Hector, to interrupt you.
I was only thinking on the positive side of using observations. But you're right, because we have to check
increases very significantly.
Okay. But continue because I guess there are also more.
No, it's only I'm mentioning that because I guess we didn't mention the question of that we can have more area in that case, and because there have been already one question about this observing mode without filters.
I guess you can go deeper also.
Yes, that's the other. I mean, the potential is to discover new objects.
Yeah.
Maybe kind of main observations.
Okay.
But
in the calculator there is an option to go open to be unfiltered, but this has not been tested in observations because we haven't. So this is a special need. So you plan, and I will write to Adriano because I guess he couldn't be here today, but I will write to Adriano that if he plans to do that, write us. He needs to, or he should write us as far as possible for us to think if this is possible or not. If there is if no one contact us, we are going to forget about the open option because it's not as easy as we think. And about the area, I don't know if it's a longer area because at the end the size of JPCam is the size of JPCam and the strategy.
No, but we are not trimming we are trimming the images now because we have the baffles that are there to prevent reflections from the filters. So we will get the full CCD area for each of the 14 CCDs.
Yeah, but anyway, you would need to cover the gaps. So then the strategy is the same, but the strategy is the same.
But you will change the step. Yeah. So you will be faster because you have more area in each CCD. So you don't need to move that much the pointings to cover everything.
Yeah.
So in the end, it's more significantly more.
Okay.
For covering area.
Okay, but well, if you plan, contact us. If not, we will and contact us, and we cannot assure if this will be possible. We would need to do some tests. Okay, and more special needs. I have here. I just notice also, for example, if you want to observe exposure of more than 300 seconds, remember just 1/3 of 300 seconds. If it's more, also if this is a special need, contact us because we will need to be sure that this is possible. We still are not sure, and we will. If there is no need, we will not test it. I guess until we have the time and the need. This is. I don't know if someone thinks in another special case.
Can I just
Yes.
comment on that? The 300 seconds is because we haven't commissioned the auto-guiding detectors yet. So this is happening in this call, but keep in mind that in the future calls, we will have an auto-guiding system, so the maximum exposure time allowed will be, I expect that to be much higher, because we will have the auto-guiding system working. Now we are operating without auto-guiding system, and that's the reason for this. I just want to encourage them to think not only this call, but the next one.
Yeah.
The next one, the performances are expected to be better.
And because we didn't have the need to observe that much time, but I think we can observe more, but we didn't check it because we didn't need it. But is anyone thinking in a different special need for your observations? No, that's good or bad. I don't know.
I have a quick one.
Yeah.
Will you accept target of opportunity programs?
I
opening the Pandora box.
I don't know.
The short answer will, in my opinion, is that we will do our best. So we will try, but again, it's going to be shared risk and also the tools to have a quick response to any trigger have not been developed and tested in this telescope. So the short answer will be we will try to offer target of opportunity calls, programs, and we will do our best to respond in the most appropriate way possible. So yeah, we are trying.
Okay.
Yeah.
But is there any scientific case to use, for example, the narrow band filters for a target of opportunity, or just or people using this is using broadband filters?
I have no plans for that.
Okay.
I'm just trying to open the programs, but I think would be broadband. Maybe.
Okay.
Let's say gravitational wave search. Well, the problem is that light was stopping for that.
Okay.
But maybe other kind of transients where you need a better location, quick. That could be an option. And quick means not very quick, but during the night.
Well, I think JPCam in broadband would be a very good instrument. We can go fast to cover a very large amount of area in broadband. So I think we should. and this is my personal opinion. We should allow for type of opportunity with broadband, and we should do our best to do it.
It would depend on if the event happens at days where we have a broadband installed, because we cannot install it for the.
Yeah, you're right.
Unless it happens during the day, I guess.
The open position is always installed.
Yeah, but we cannot focus.
But just thinking in poor weather conditions here, that the target of opportunity might be willing to cope with a trigger in basically any condition.
And maybe we should always have a broadband tray. Yeah. Or open. I mean, open. We are not sure. One, if we cannot focus, doesn't matter. I mean, at the end, it doesn't matter. You will have a worse PSF. Okay. So all of this should be, I guess, discussed by us, and we will try to publish and to make this clear. Thank you for the comment.
For the GRB community and people working with the extreme proof, transients could be of interest to do this. So just think about that.
Yeah. You said all the filters, no?
No. I think they need to find the counterpart, let's say.
Yeah, so it doesn't matter that much the filter.
Yeah.
Okay. Maybe also the PSF is not as Should it be important? But if they have a 3-second PSF, I guess. Well, anyway, we would make this. I hope we made this clear in the call. So somebody, I will take notes because this is important.
Maybe just like whatever broadband is installed in that date will be the one observed in the target. So maybe there's the green tray for some other program, and then you will get the green broadband if it happens on that particular night. And if it happens on a night where we have the I band, it will be observed in I band instead. Something like that.
Okay. Any more suggestions or comments? If not, we will plan your proposals now. We will. Okay, let's move to the planning of the proposals. I would like. I mean, probably I would like to start with the Rana's idea, just to start playing, and we will. Or if anyone has a particular need to check the planner and the exposure time. Oh, let's start with Rana, and then I will move whatever I think. So let's, for example, where is it? This here. So okay. Remember, this is the JPCam exposure time calculator. So, Rana, how deep do you want to go in which band? Just so, I mean, don't. It doesn't matter that much. So, remember that JPass is between 21 and 22.
Up to 22.
Up to 22. So, let's try what magnitude you would like to go. What? How much?
I know in surface brightness level.
No, yeah, but be real, realistic, realistic, Rana. I can put here 30, but I can put here 30, but I mean, I know the result is going to collapse. What? No. As much? I mean, 23 maximum.
How deep do you want to go, which is less than 23?
Exactly. Yes.
Try 3 or 5 times deeper than normal.
So this is 24.5 or well, 0.8. Okay. Let's see. And so
J0 400.
okay. Thank you, Rana. Okay. So and then this filter, I guess, is in tray 1, but I don't know now. Of course,
T4.
34. Okay, 34. Okay. So let's. So sigma, let's go 4 or 3. Or 43, no. Yes. Yes.
What happens if you put a filter on top that does not coincide with the tray that you're choosing?
It's going to show. I mean, so if you choose tray 4 and the input band is not in tray 4, the calculation is going to be performed in the input band, but it's going to show all the filters of tray 4 and probably input band. But now I'm not. But the calculation, for example, the signal to noise ratio is going to be estimated in the input band. This is just for output plots. But thank you, because I probably need to clarify all of these points. I just build the tool and then I guess that I know that it needs to be more clarified.
Yeah, it's fine. It's just.
So you do a for dither pattern. Okay, probably your object is extended.
Yes.
But let's check, because what you are asking is just to increase a little bit the depth of JPass, and the depth of JPass is in non-resolved manner. So well, then we can play with when you know how, if you would, when the people or the or the team know the limiting magnitude resolved, you can use this. But let's just going a little bit deeper than JPass so it's not extended. Let's Ermas the best, binning, because this is this is in narrow band, so we use binning 2 and dark, of course, and even though you can put here an AGN or a Galaxy, AGN. Okay, now, the problem, no, it's not a problem. Let's put yeah, but the problem with this is, I think it's not the whole range in wavelength, but anyway, let's. Well, because I just took it from a library, so the library is
6,000 angstrom.
yeah. It's just because I didn't do this template. I just took it from a library. I don't remember now, and it's not complete the whole range. But always, if you know a template or whatever is useful for you, you can send me and I can include it, or just you can put your file. But I'm very happy to receive your templates, and at the end, what we should do is to do a tool to build the PySynfo readable format. So work in progress. Then calculate. So it's not that large, so probably we can go deeper. Again, here the input as the quasar template is not the best one. Let's change. Let's put a cipher 2. I know that probably is not a cipher 2, but is. So you would have a very good signal to noise. But let's go to 5. No, for example, a 5 signal to noise ratio. Okay, 100. So you can even go deeper. Let's go
10 times deeper.
Okay, so let's go 10 deeper. That probably is going to be very high, but okay. So it's still doable. In fact, JPass in this trade, JPass observed 480 seconds. So I think I'm not because of
split in eight exposures.
what?
No, 4. How many?
It's 4, yeah.
It's 8. In Egypt, the 4 figures is
Yeah.
8.
Yeah. It's probably let's and for example, Rana just want one pointing. No, probably this is
Minimum 1 point.
minimum one pointing. Okay. Now we will go to the area.
Plus
Okay.
so it's one for the line, one for the continuum.
Yes.
Okay.
But maybe that can be integrated in the normal differ.
Now we will go to the area. So let's even go deeper. Let's go 24. At the end, the scientific case should be decided by the teams, no? And we don't need to define now the time. We are just playing with, no? At the end, I guess there are some data about some zone or some similar object. So I guess, based on the data available or similar objects, you can think how much is the signal you have, the magnitude. So let's go 24. This in fact, let's go with the maximum. Let's go with the maximum. The maximum. Someone remembers which is the maximum? I told yesterday.
300/4.
Exactly, 300/4. So thank you, Andres. Okay, and let's look for so we can even go deeper. Okay, now for the 400, you reach this 3.7 signal to noise. Well, I would like to have maybe at least 4, no? For example, the 4.1 is a good signal to noise ratio in your desired band, which is the 400 filter. Okay, so now we have the exposure time, which is 120. no, 100, no, 1,200, sorry. And then let's go for the area. The area you call Lyman Alpha. Well, I guess you know the coordinate you want to observe. We don't, maybe we don't need that right now. So let's go for this. And you want tray 4, is the 400 here? Yes. So let's remove all of them. You want the continuum?
Yeah.
The continuum, for example, in 440, okay. If you have the continuum in both, would be better, but 400. But I don't see here the 3, okay. So in principle, these two filters, let's go with this one. Also, I don't know, just for playing, no? The blue filter, which are in the center. We center your observations at the filter you want, and then you can make a 1 by 1. Or no, a 2 by 2, because you already have said that you need the continuum. Addiser, official, okay, okay. Well, here, your common area is here, the center is here. Well, we at some point we should define the right pointings with our support. In fact, I can improve this tool because right now it's not very clear even to me.
So this means the two filter over here.
If you select the center at the JPCam center.
It's better because they are the 4 filters. Thank you, Hector. Yes. Thank you. Yeah, that is closer, but this is because of the differing pattern. But don't worry, we could play. Well, you can change the coordinates here, but also I need to. This tool is going to change to center this better because of the differing pattern. Just give me, for when we release the call, I hope this is going to be ready. But so let's think that Rana can center this in the object of interest that she can, and we will do it for her, and it's not that difficult. But so the important thing here is that the common area with default filters is 0.01 square degrees. So it's not that big. Maybe it's enough for her or for her project, but also, for example, maybe she doesn't want these two filters that I put because I just wanted, but maybe she just wants these two filters. No? So now it has a more coverage. And remember, you can download the DS9 rec file to check where this is. Let me there will be a change in where the central pointing is. But at the end, the proposed or the team should play again with the coordinates because it's different. The JPCam center and the center of the filters, the center of the common area. This should be also. So there is some place to play with this, and probably you would need to change the coordinates. But
so these two filters are actually minimum requirement. If I have the filter covering other lines, like for example C4 helium-2, it will be great. Yeah.
And in which so at the end, which filter you would?
For example, in this redshift range, 510, not in this tray.
Okay.
510, 500 will cover C4, and I think 630 will cover helium-2.
Then you should talk or you should ask for to define a tray. Probably we are not going to make happy everyone about this distribution of filters, but well, you can ask more trays or okay. And Stelios?
I'm not sure if I'm missing something here, but let's say that Rana is a galaxy, right? And it fits in one CCD, and she's happy. It's a smaller one, and she's happy with the area around the galaxy that it fits in one CCD. Then and she wants these two filters. Then you just observe the galaxy, and then you center this galaxy in your next CCD. So your common area should be one CCD.
Yes, you are right, Stelios. you are not losing anything. The best way to do this, if Rana wants this, the best way to do that is just, there is no need to use this tool to plan the pointings, she just needs 2 pointings.
Yeah.
So yes, you are.
Okay, inside you can have the dithering if you want, or even,
Exactly.
If not, that depends then on the reduction.
So
you need the dithering for the reduction, so you can dither a bit around.
So,
yeah.
And the thing is, it's not like one target or something. It's like at least like in certain range, or redshift range, I can have the different QSO at different redshift range can fit in the different filters. So it doesn't matter, like should be, it is not for only one target or something. It's like a search for the QSO, and I already have done with the JPAS. So I already have the target, but I need more deeper observation.
Yeah.
So it's not like a 1 or 2 target, it's a range of, in different range of redshift. For different filters can cover different redshift of QSO.
Yeah.
Doesn't matter. But at least minimum I need this, because I have an interesting target that can cover in this filter.
Yeah, of course, remember, if you ask for this, for example, if you ask for just one filter, and I just also well, I don't know if you are going to understand this, but I will try to explain myself. Because it's not that easy. If you don't use Dither and you use this tool and you center the JPCam, or the observation in the filter, you will have, of course, the central coordinate you include is going to be centered on the CCD. But if you use Dither, which is highly recommended and supported, and you compute, now the tool is not ready to put the center of the dithering, the common dithering area in the center of your pointing. This is not difficult. I didn't do it, but at the end, I hope that in the next weeks, if you use Dither, which is the supported option, and now the center of the common Dither pattern will be in the center of the coordinate.
You said, in this specific case, that's not needed. Because you don't need to do
the balance instruction.
No, forget that.
Okay, but well, this will be changed in the following weeks. Okay, if you use Dither, then I hope you can center on wherever you want is centered on the common area of the Dithers. This is still, I didn't have the time. It's not difficult, I think, but I didn't have the time to put it.
Then that would change your effective common.
No, exactly. It's going just to change the pointings and the visualization. Yeah, the common area is going to be the same, so play with.
Well, in this case, no. If you would want the galaxy node for dithers, which you probably do, so that you don't lose exposure time, then basically you would end up discarding a bit. Right, it's not going to be a full CCD, right?
Yeah, quarter. It will be a quarter of the CCD.
Yeah.
Based on the, because the dither part that is half a CCD. So basically you would have a quarter of the field of view in the center.
And one important thing, if you ask for this, I think this is a risky proposal, but this is my personal opinion. Here we have 2 persons from the CAT, and they may make or if you want to, now that you are here, maybe you want to comment on this. I know that it's risky to ask for this, so do you want to say something about a proposal like this that just use very small amount of filters?
In my opinion, if the science case is solid, I could see a good justification to observe in this mode. But it's true that on the first order, it will look like, like not getting the full possibilities that the telescope offers. But this really depends only on the science, not.
Maybe you don't want to comment. I mean, I don't want to make you.
Is the only proposal?
Okay. Okay. From the first. Okay.
So we changed the name of JST to Rana's personal telescope.
So then, what I would encourage is to try to make this a larger project, like use the other CCDs to do more things and to join people, or I don't know, to make this, or I don't know, maybe I don't know exactly the science case, so we don't know, but it's just to warn the people, this is risky. This, in my opinion, this could be risky if you just propose this. But of course, all of us, we want a deep field. I mean, it's very interesting to have a deep field. Yes, I want. I mean, it's not efficient, but I mean, it's great. You go deeper, you see more interesting things. I mean, it's obvious. You can laugh, but it's obvious. It's very it's very it's very interesting. Of course, we are not the most, or probably is not very efficient because of the growth of the signal over time, because it goes with the square root. But I think, well, I would like to see, in my personal view, I would like to see a deep field of JPass at some, or with JPCam at some point.
May I comment?
Yeah.
I want to comment as a reminder, it is not a new thing that we were mentioning, that the question of the dithering. It's a reminder why this is important. If it is important for you to correct from the background features, some dithering is needed. Why it is needed? Maybe in my talk I didn't make this point clear. We are masking the objects. If we don't have observations with the objects on different positions, there's going to be holes in the final mask, so we cannot assess the background there. So we need to we have to move the object, so we have in the end signal for the background in all the area of the CCD to assess the background and then remove it. So this goes as the size of the object you are interested in. So if you are interested in large objects that may be impacted if you remove the background, you need to make a larger dithering. If you are only dealing with stars, then maybe a small dithering is enough. But it is just a reminder. And we need not only just a dithering and that's it. We need some, in order to have enough signal to assess the background, we need a number of images to actually assess it. So, so we need observation of the same filters with the same similar conditions, so we can model it. So, just for you to keep in mind, if the background is important for you.
Now let's go to check how much time, for example, this risky project, because it's just it just uses one filter, but probably we could use the other filters, or to imagine some other science case using the rest of the filters. I don't know, or think in larger, no? But anyway, here you just need one pointing in tray 4, and the exposure time is this. Well, you need just one, and then, well, you should multiply by 2 because you are going to move. So the total time is less than 1 hour, and I guess you should multiply by 2 because you are going to propose, and you don't need the planner, but you need another pointing, so you need twice this amount of time. So 1.3 hours you need. It's not that big, but so maybe people is interested in using just one filter, it's not a lot of pressure in time, but I don't know. It's possible to ask for it this, and then you just need to convince the the evaluation committee. Okay. I don't know if I did something wrong. Stelios already clarified to me that that you don't need to use the observing plan. Yes. So this proposal just would need one, no, two different pointings, but defined.
Well, need to use your plan upgrade
Yeah.
of
Yeah.
planner.
And if you have doubts or questions, please contact me. Okay, and if you find strange things. Okay, so this is the run as.
One thing that I wanted to just going back to your question before. So, it's true that one important point here is to demonstrate why you need this particular telescope. And this is a very important part of the scientific case, right? Why do you need, even if you are observing with just one filter, why you need the field of view, whatever and that particular filter that it's only available in this observatory. But and this is just my personal opinion, if there is a proposal that uses just one filter, but it requires this field view, and it happens that the T250 in the OAG is the only observatory in the world that has that particular configuration, well, it is what it is. And I will consider that if the science case is solid, I don't see why not. Even though it looks like you are not using the full capabilities of the observatory. No. This is something that it has to be regarded from the scientific point of view, more than from the technical.
Thank you, Andres. And of course, this is the convince the cat is always it's always hard. I mean, no, we are not going to. Opinion, this is.
There must be other members that different.
And this is again, this is something we are not going to solve here, no. But it's important to. I mean, what I don't want is to encourage people to just ask for one filter. I don't want to. Okay, another project, for example, let's go for David Morates project. So how much deep you wanted to go?
Well, in principle, since I don't want to go that deeper, worst case scenario, I think it would be 390 filter, 19.
But for example, do you have a filter? Well, I don't want to go to the worst case. Let's go to the.
Worst case scenario would be this.
Yeah.
And
the
rest of the things will be that.
Okay, and
I would say 19.
19. Okay, so 19, and you want to do this in one whole night with is tray one.
With this thing.
Oh.
And please put all.
All the trays, okay. Okay, I had also the answer. Change trays is, well, of course, it depends on where are you exactly pointing, but it's around 7 minutes and a half. Well, sorry, I was talking with Tony about that. For me, when I'm there, it likes to me is almost 20 minutes in my mind, but because when you are there and you think you are losing the time changing trays, it seems longer, but it's 7 minutes and a half, and not 20, as I said yesterday. But this is not this can change. It's plus minus 2 minutes. Okay.
So in here, I would say that around 40 seconds.
Okay.
This would be like 4 exposure of 10 seconds.
Yes. And to make this clear also for the remote participant, this means 4 exposures of 10 seconds each, and D-third. So it's D-third, so it's 4 exposures to do D-third, I guess, because it's narrow one. Okay. So being 2, okay.
Let's put bright.
Yeah, because it's not, okay.
And if you want, since we are going to be observing something that reflects the sun, you can put stars on to be.
Is like this?
G.
Okay.
You put G0?
Yes, but no,
in any case, if you write G, it will go there.
So it's a very good signal. Well, you can even go deeper to check potential.
If we can go deeper.
Claro. To see potentials dangerous asteroids, because if not. Okay, well, this is the very cool. Well, it's 5 in this blue. Maybe you want to go. Well, yeah, because at the end you are interested in, well, in this, no? So for, no, let's go.
I'm more interested in the region.
Okay, so let's go. Yeah, let's go deeper in. Okay. Yeah. 3.9 in the Ujaba, but this is the, well, this is.
Is this just for what we know now about?
Yes, this is already correcting that effect, but correct. So yes, it's like realistic. This is contrasted with JPAS observations, but well, it can.
If we can go that deep, it's even better.
Okay.
I would be okay with something.
Okay. No, maybe no, just to.
Mind that we are taking the ocean for right.
Okay, so you can go 6 signal to noise ratio 6 at with this, no, at 19 magnitudes, and then with not so blue filters you go. Okay, so let's. In fact, I mean, this is important because you don't need to use the same exposure time in all the trays. So, well, just also. Yeah, but the worst case is the Ujaba. So just expose more time in tray 1, and then the other you can exposure less. But well, let's go with this just to check how much time you need. So and how much was the?
I was playing yesterday with the planner, and since I'm more interested in sector say, I'm interested in the more blue region. I checked having only the common region for only the central filter.
Okay.
To give me a common region around 4
Okay.
something square degrees.
But how much is how large is the mosaic? How many? 6 by 6. Okay. 6 by 6, and then 40. Yes. Okay. And no broadband. So well, yes, it's like, well, 3 hours. You can do this also in another field in a different night. Also, I mean, if it's a field, no. So if it's a filler, I mean, there is going to be less pressure, I think, in this bright time, David. Or I don't know, but we cannot. We cannot. Well, we don't know the future, but but if I mean.
Because yesterday, for example, I was using I didn't know what the beginning should be 2. I was putting 1.
Yeah.
It was giving me worse.
Yeah.
And I was using a higher exposure time. This configuration, the exposure time that I would need is smaller. Total time on the break will be smaller for one field. So I'm starting to think that it's no.
Yeah.
And also the thing is that in the common region for the filter, there's a smaller region around 0.5 square degrees that's common to all the field.
Yeah.
So I would have information for a lot of
discussing during the coffee break that surrounding that region of all the filters, you will get a lot of filters. So if you're not particular about which filters you want outside of the blue ones,
I mean,
you just want some information there.
I've been constructing spectra with 7 filters.
Yeah. So you will get a lot.
I don't mind if I have 20.
You will get a lot of points
Instead
there.
of 54.
So you can say in the proposal, thanks to the magnificent design of JPCam.
Okay. I think that's good for if the observations took around, let's say, 4 hours. is that it's a good, how do you say this? It's a good time, exposure time, total for to have efficient spectral capacity.
Yeah,
For example, if the time is longer, maybe what we were talking yesterday, the rotation periods of the answer will start.
okay, affecting. I have to clarify that in this case, I forecast that the total time is going to be larger. This is not right. These 3 hours are going to increase. Unfortunately, I don't know how much, but it's not going to be the double. I mean, no, don't worry. But yeah, yeah,
Even 5 hours.
is okay, okay, okay. Okay.
Will you play was for the 4 trays or just 1 tray?
This is for the four.
For the
Four trays. Yeah, yeah.
Also, something I commented yesterday, I thought of it a bit more regarding the number of exposures needed for the super background, because you will have a lot of low exposure time images. Maybe it's also enough. Like we are dividing the night in many chunks. That would complicate in JPass the exposure, the super background, the master background generation. But if you have so many images at different locations, then we will also be able to do the super background for this project, I think.
Maybe it's a good time for commenting that actually the background is more significant in the reddest filters. So in the bluest filters,
Yeah,
maybe it's not even needed.
yeah, but if you want to make use of the extra information you will get for the surrounding CCDs, not just the blue ones.
For the peripheral CCDs, it's clear, but maybe for what you are most interested in, the blue ones, the impact is much lower.
So I would encourage you to talk with Hector's and and Dipat
We have another director if you want that. Engineer,
because if we can forget about the distance in this case, it would be the area would be larger. But again, I would encourage because the more or the problem with this project is that you need all the observations in the same night. So, but I want you propose more nights. So you should think in more fields, I think. But anyway.
Listen, yesterday I think that the total time was around 200 hours.
Yeah.
I don't know how much would I be able to ask if it was a filler project.
Yeah.
Of course, I know how filler projects work. And
Yeah.
time allocated might be all, might be half.
Exactly.
Might be small. But I will propose something.
Yeah.
Then I will move according to that.
But in practice, the filler in all the observatories, in all the telescopes, the filler programs are the ones that sometimes, I mean, if it's a real filler, they are observed the most. So, so, okay.
My thesis was based on filler.
Okay.
we don't want to tell that, but I think you can say it. If this can be done in right time, this won't put too much pressure to.
And one other thing that I was thinking about, Tony said yesterday, if the field that we're pointing to is
Closer to the center.
Yeah. The time to change trays is smaller, then
Yeah.
it will be more efficient. So that's another thing.
Yeah.
I'm starting to believe.
Yeah, me too. Okay. I don't know if it's dark. I don't see, for example, Elena's here, no? Because I listened. Well, the other day she shared about an Arrakis galaxy, but Mohammed is here. I don't know. Maybe we can.
Few large nearby galaxies that also form an Arrakis.
And then if they're sufficiently close to each other to fit, like let's say in a 20 degrees square area, then yeah, that would be a nice program for to go very deep over many years, not just one, to cover all these margins. Oh, that's gonna take. I don't think in this round. Maybe in next year. Maybe next year. We'll look into it.
But well, a pilot project or for one galaxy, I don't know, Mohammed, I'm just.
We should find, so we have a mission directly sample, and we should check which ones of them are nearby, so they can fit in this, so they can fit in one project of JPCam.
You would, but are you thinking in all the trays, for example, with all the filters, or so you need all? No, this of course, it's if you are talking with.
Cover them before 2030 when Atlantis is launched. But no, we want some.
Okay, but let's play, for example, with a dipper. No, I mean for a dipper, because we know JPass is going to do a lot of things, but just to explain the use of the, or I don't know, to explain and to encourage you to ask for a small project. For example, you don't need maybe to a very large area. Let's go for a 0.5, a half square degree, which is a 6 by 6. This is going to depend on declination, also on the, maybe you want a crazy desert pattern because because you are interested maybe, but well, let's go for our supported desert pattern. This maybe depends on the declination. If you go very north, it's going to change. Or anyway, let's go, because I know we don't have an object, but if you want to do a 6 by 6, just a 6 by 6, how much time it will take, and let's see if it's reliable. Okay. Okay. Okay, so let's go 7 by 7. Thank you, Mohammed. So, for example, one and a half square degrees, which is a 7 by 7, and you want to go very deep. Let's check. So I know, well, let's put 24. And so, of course, I'm going to cheat. I will choose a filter that I like. I don't know, that I know that, well, no, if I choose a blue filter is better. Anyway, let's this one. And you want all the trays. And for example, let's go for the maximum. Probably is too large, but it's not this. I know this is not going to be possible. And then a maximum of exposure time. So we are offering the 300, so it's 1020 divided in 4 exposures. So, and then let's choose a galaxy. I don't know which type. Okay. Okay, spiral. Okay. Let's consider receive one. So, okay, with the maximum time. Okay, it's not it's not very deep at 24, but maybe. Well, and this is punctual, so I guess you would like to go extended. I know. I mean, you have an extended. So you would like to check. Well, let's go to extended object. So 23.5 magnitudes per second. Of course, this means nothing for you. I know. I mean, I know that this is very little, or this is very shallow for you. But anyway. And well, and then you can play with. I mean, the observation is with this binning, but then of course you can bing, no, for the stellar streams, I guess, but depends on the size. You can go deeper in larger regions. If you use GenWastro, you find, no, the best results. But well, okay, let's see how much. Okay, so this is the signal to noise ratio in some between 4, 2 and 4. Probably you want more, but no, it's extended. Sorry, it's extended.
Extended over what area?
No, over the binning, so over 2 by 2 pixels. Okay.
Okay. No, this is fine. I mean, if on a 4 by 4 pixels, 2 by 2 pixels, we have a similar.
Okay.
Over thousands of pixels, we have.
Okay. So, but then let's see how much time it takes, which is going to be it probably is not feasible. But yeah, but we are not going to see only the feasible projects. Well, it's 130 hours, so it's not for this. Well, but you can go well. Let's yeah.
Because the spectral resolution is more important than the spatial resolution. I mean, if we can have a back PSF9, we can, I think, go to the back PSF9. It should be dark, and we don't want the moon to be too close, but if the PSF is bad, it should be sufficient because we're interested in the diffuse regions. So maybe, maybe that, if we allow that condition, can it increase, you think? Possible.
The
Developer time is 200 hours.
Well, but for darkness.
No.
Okay. Yeah, this would be a big waste. I mean, do you also have the area around it? Because they have two degrees squared, the area with all filters.
Yes.
Then you get a huge area around it.
Yeah, just all this area, yes. All this area would have some observations.
Yeah, it feels bad.
Yeah. Well, but at this no, but in this call, all the projects are going to lose. All projects are going to lose some area. All even JPass is losing some area. So remember, the more area you use in common, the better. But all of the projects are going to lose area because at the end, we are not in 1 year. You are not going to be able to go all the time to the same field. So it's important to realize that at the end, the maximum mosaic, the realistic mosaic, and depends on the period of the time we can observe that particular field. We are not going to be able to do a longer. This is not a fixed number, but probably we are not going to be able to do a 10 by 10 mosaic. There is no time to observe during, unless you do a very small exposure time like David Morate. But I mean, it's very difficult to do a large mosaic like a 10 by 10 for all the trays. Which is the most efficient. So what I want to say is that all the projects are going to lose area. So don't be afraid of not using all the filters. Of course, at the end is an intermediate point. No, don't use just one filter or yes. No, it's no one is preventing you from using just one filter, but. And of course,
reasonable amount of time. To get an estimate.
And now for I don't want to make this announcement in part, but for the people in CEFCA, also talk to me about a deeper field. Because, well, just talk to me about a deeper field. This is an opportunity for them because sometimes we do tests, and so we can do these tests in your fields. Not because if I have to do a test, at the end I do it in whatever I want. But if you have deeper fields, but this is not going to be guaranteed that it's going to, because they are tests. But for the Rana, Mohammad, or whoever wants a deeper field, we can use those fields when we do tests. Yeah.
I'm sorry, unrelated question. I don't know if this has been mentioned or if it's said
if it has been mentioned, I missed it, so perhaps other people missed it. When exactly will the observations for the open call start, and how long will they be for?
Yeah.
That
So
obviously affects your target selection.
yeah, yeah. Our goal is the following dates. So yeah, they are here. Yeah. So the period offer will be. This is our goal, and then I put here a disclaimer. Our goal is to start to observe in the second semester of 2025, and then continue this observation during 1 year. And the call will be released. Our goal is to release the call on February, the next February. Yeah, but this is important, and this can affect the targets selection, which is that we expect a shutdown of 3-4 contiguous months. And of course, when we know these dates of the shutdown, we will also publish them, I guess. And in my case, I don't have more examples, unless someone wants to try something. If not, please send feedback and suggestions on how to improve the tool or the tools. Okay, that's all from our part, I guess. I don't know if someone has. No, you.
Well, I was about to just to trigger more discussion, but
Yeah. No. Sorry. Yeah. We have time.
For the M31 project, how many pointings are needed, or how many time is needed for M31? I don't know if the exercise have been done already or,
No.
or not.
No. Borja, do you want to tell an area for the M31 project, M31, M33?
Okay, well, we can find 4 minutes.
No. Well, yeah. Well, fine.
How many pointings? Okay.
No, or the area.
So you were saying yesterday, like, for a pilot survey, like, it was like 6-8 degrees, square degrees.
Me-
You were discussing that.
Yes. Well, yeah, it can. So a 9x9 with all the filters, for example, and
So how many pointings? would be-
yeah. So let's. Well, it's almost 5 square degrees. With a 9x9 pointing, you have almost 5 square degrees with all the filters in. Well, yes, with all the filters in common with one tray, and then you repeat the process for the other trays. So the pointings you need is well, a 9x9, which are 81 pointings for almost 4 square degrees. Well, this can change. Depends on declination. I don't remember. I don't know the declination of Andromeda. Sorry. Do you?
Declination is like plus 31.
31.
Just the declination is,
Yeah, exactly. No, that's the reason I was. So it depends on declination. So let's go.
Okay. The rest extension is 1 hour 30.
Okay, but it doesn't. The problem is, well, the problem or the effect is on declination, and it's not that much because, as we can see, it's almost 5 square degrees. Well, so this is with a 9x9, and if you want the same depth as in JPass, this means 55 hours of time.
55 hours.
55 hours.
Or 5 degrees.
What?
Or 5 degrees.
Yes.
Square, because maybe I don't know.
Yeah.
Maybe you can play with other shapes aligned with the shader.
And you have to check, is your field or your particular field observable during a large enough periods of time to observe 55 hours competing with other projects like JPass or so. Also think about this, because maybe you can go by 9x9, but say, okay, but with an 8x8 we can do like this science, and with a 9x9 we can do this other, no? science. Or so also be flexible. Like well, this is a recommendation. Even I 7x7, no? Probably with a 7x7, we can.
Okay, well, when I will be starting to play with this tool, will it be possible to just to go to talk to you?
Yes. And I'm very happy to receive suggestions and comments, please. I mean, yes.
There will be questions more than.
Okay. Okay. But for example, a 7x7, it's because you can ask for a 9x9, but then we don't know if we are going to observe a 9x9. But probably know if with a 7x7 you already have some science, although you lose a lot of information here with all these filters. But if you do some interesting science here or whatever, it's also, I mean, it's also possible that although you ask for a very large mosaic, because this is a pilot, is going at this day. We know that we cannot not observe all M31 as you saw yesterday. But if a small region can be observed as a pilot proposal, I think it's very positive.
Okay. Cool.
And let's, for example, let's see a 7x7, how much time it takes. Do you know, or I mean, probably you don't, but let's just to use a number. So the depth, we would like to go in Andromeda at some. So Andromeda is SA. I don't know what morphological type is Andromeda.
What is
Spiral? Spiral, yeah, but it's A, B, C. S. No? Okay. Let's go SA.
You're trying to get the stars.
Okay. Thank you. So which stars are you more?
Trying to get the stars. So can I tell you how deep I would like to go?
Yes.
For example?
Yes.
I mean, let's see what happens if I want to go to 25. Let's try to go for the best.
25 as well? What are you?
25 in the narrow bands or in the broad band?
Good point. Well, let's try 23. Let's go.
Okay. Yeah.
Let's be realistic. 25 in the 660.
Let me dream and then we get back to the.
Yeah. Okay. 23. Well, I'm going to put a blue because no, a red one. Okay, I'm going to cheat. So 23 in the red, for example. Okay, all the let's.
That time, I guess.
Yes. And then let's go for. I'm thinking. Let's 600 seconds. Let's go for 600 seconds.
10 minutes.
Well, but it's divided in 4 exposures.
Okay.
These ethers. Being in 2 because it's narrow band. And do you want to put a specific star? Like a stellar type?
I think you will be dominated by KM giants, I would say.
Okay. Let's. Right. So. Boom. No. Anything. No. Let me. No. Anything happen. Don't worry. Let's go. I just made a mistake. Okay. Well, this depends a lot on the selection of the input band. So because this is normalized to the star you input. So you, for example, you want to go to 23 magnitudes at the blue. But then you with this amount of exposure time, 600 seconds divided in 4 exposures, you have a signal to noise ratio of 10 more or less in the 400 filter. Of course, the problem is this depends on the signal to noise ratio, or the signal measure is going to depend on the flux, on the wavelength. But let's just focus on the 400. 400, you have a signal to noise ratio of about 10,
okay,
with 600 seconds of exposures at 23 magnitudes. Oh, sorry, I did something. we are going to resolve the stars.
Yes.
So because then I forgot to change the, sorry, it was wrong. Okay, but the end is similar. Signal to noise ratio of 9 for an aperture of 3 arcseconds at the 400 filter, and the signal to noise ratio for a star of 23 magnitudes in this band, in 4,000 Armstrongs. Okay. So, and let's see how well, and because I have here that because it was the example of Arrakis. A 7x7, it takes for this magnitude, a signal to noise ratio, it takes it's the same. It's 65 hours. So I don't know. It's very large. I don't know. Experience observer of M31. I'm looking, for example, at Alessandro or Hector. Is it possible? Is Andromeda visible during enough time? Oh.
It's good, but it is low reclination, so the moon is affecting a lot because it's whenever you have the moon is always near the target.
Okay.
So in that sense, it's not good. But in terms of visibility, even that is low reclination, you observe like maybe 4 months or around 4 months.
Right? I mean, studying these lines are worse.
So I think it's like a normal touch. It's not excellent, but it's not bad. It's medium.
It's actually on the good side of the southern part of J pass or J plus. So it actually normally is the good thing to observe in this is among the good things to observe in this season.
So I'm not saying we shouldn't observe Andromeda. What I'm saying is what is the magnitude limit we will reach. So in fact, I'm just reducing now I'm changing. Well, probably 600 seconds is too much, or not. I don't know. I don't know if it's too risky. We have to, but if you reduce the exposure time, then you will have a shallower survey or observations, and then of course you will have 50 hours.
I missed it. Are you doing in bright time, gray time?
No, dark, but I just changed this, the exposure time to 480 seconds, for example. Like.
Very interested in going deep in this case. I mean,
What?
the more the better. I mean.
Yeah. But the problem is in 1 year, are we going to have 50 hours to observe Andromeda? This, well, it's something that at the end is going to decide the CAT, the Time Allocation Committee. I'm just playing. At the end is the science you want to do should be the driver. I'm just playing with the exposure time. But at the end, you have to check which questions you could answer with which magnitude in which band. And of course, we are here to help the people. And Borja, if you. Well, we will be in contact.
I'm going to play with these tools like by myself.
Yeah.
I'm not sure I will go to your.
Okay. Okay.
Yeah.
More cases. Okay.
Because I'm thinking, for instance, in a strike with certain inclination.
Yeah.
Can we rotate the camera, or we have to play with different?
So you have. Yeah, I think this is related with that, but with what Hector was asking the other day, but then I understood this later. So you are thinking on planning the pointings with some inclination?
Yes, for instance, kind of a strike.
Yeah.
Pass.
Yeah, this is not straightforward to plan. So this would be considered as, I mean, this is not supported right now. This is not possible to use this tool to use that, because if you change the inclination,
Because if you can rotate the camera,
yeah.
the estimations are going to be the same, but the point is changing.
Yeah, but then
The theory, if you can rotate the camera, I think that is going to be.
But not only that, the problem is also the planning of the pointings. Is
Yes.
well, they are not prepared to be rotated. It's possible, but we are not. We don't have the tools to build. Or maybe well, I don't have them. I don't know if because Hector has worked.
If you rotate the camera, you will have some effect on the projection, because again, this is a mosaic of 14 CCDs, but they are monolithic, no? If you rotate things and project, things change a little bit. So this is just that we didn't have included the rotation in this tool, but it's something that is doable, but we have to think on the implications that it has in the operation, in the data processing. So it's something that for sure the telescope can do. We did it with JPCam, but we should have all the aspects that imply that rotation to be assessed. But
Yes. So if someone plans to do that, just contact us, and then we can check if this is something possible. This is something we haven't done, and it's doable, but it's not straightforward to project. At least for me, and the thing is, right now I'm the responsible to plan this, and for me it's not straightforward to rotate the pointings with the and be sure that they are right. Of course, I can I can do things, but to make sure that they are right and they are efficient as these pointings is not straightforward for me. Then I don't know if there are implications for the data reduction. So that's the reason that if you need this, contact us, and then we would discuss. Our department we would discuss and check if this is possible.
Just an idea.
Yeah. No.
Typically, this happens many times, especially when you are trying to observe a common area with other sources and so on.
Yeah. Yeah, now it's rectangular or square is the supported option, at least for this time. And the special mode as the one as to inclinate these pointings. Well, it would be special, and we need to check if we can do it.
Okay.
We are not sure. I am not sure if we can do it in this at this moment. Okay. So I guess we conclude this meeting. Thank you for coming.
Before we conclude for real, would like to thank and congratulate the members of the organizing committee. If the members are here in this room, please stand and get your deserved applause.
Thank you a lot for your help in these both meetings, in the previous one, and I mean your help has been we have made possible these both meetings, and we should be happy and look for the next big teams for the next for the next meetings. Okay. And well, thank you for those in remote, and see you.
Records.